are back to do our homework and practice on our introduction to the fundamental theorem of calculus. So we've got a mixture of types of problems here. So notice in our first problem, it looks like we're doing the derivative of an integral, so we think fundamental theorem of calculus part 1, but notice that our upper limit is not a variable. So what does this problem mean? We're finding the area under this curve from 0 to 2, so this is a constant. So what is the derivative of a constant? That would be 0. So make sure that you are reading questions, not just anticipating what you think the question is going to ask. Here in our second problem, now we're differentiating an integral with an upper limit that has the same variable. So remember, this is what we want to look for. An integral accumulates the area. So here we're accumulating the area from 87, which doesn't matter what it is any constant as the lower limit. So when we do the derivative of the integral of this function, we will return back to the integrand. All we have to remember is that our variable will be replaced. And once again, we're going to look at more proofs to make sure everybody understands why this fundamental theorem is working as simply as it does. In our next example, the difference now is we still have to check that this upper limit contains our same independent variable. We're differentiating with respect to t, and our upper limit is t, and our lower limit is a constant. So now the only thing we have to remember here is that, yes, we're going to replace our independent variable with 5t squared, but we also have to remember that we need to add a chain rule. So I have replaced the x term with our upper limit, and then don't forget that we have to multiply by that chain rule on that 5t squared. So we're going to multiply by 10t. So here we will come up with 4 times 125, 500 t to the 6th times 10t. So we will come up with about 5,000 t to the 7th. All right, and here we have a function g that is defined to be equal to the area under a curve with variable x. So again, this is called our accumulation function or accumulator. So function g is accumulating the area, and again, notice that these two have the same independent variable here, and our lower limit is a constant. And what are we asked to find? We are asked to find the derivative. So the derivative of an integral, g is equal to an integral, so its derivative undoes the integral. The derivative of an integral gets us right back to the integrand, but we have to remember that each of these x's will now be replaced with that t cubed, and that's going to again require a chain rule. So our chain rule on our upper limit will be a 3t squared. And how much you clean this up is up to you here. So we have a 3t to the 6th times a 3t squared. So we could make that a 9t to the 8th, and then, so I distributed at the same time here, plus a 3t squared cosine t cubed, or any equivalent expression. All right, so now I'm throwing in some derivatives here so that you get used to the idea of when do you use the power rule and when do you reverse the power rule. So here we're differentiating with respect to x. So we bring down the exponent and reduce it by 1. But this problem, the integral of x to the negative 2, is our anti-differentiation. So we raise the exponent by 1, and then we divide by that exponent. So our coefficient here was a 1, and we're dividing it by our new exponent of negative 1. And this is an indefinite integral. Remember that terminology. So we get a whole family of antiderivatives. So when we evaluate an indefinite integral, we add the constant of integration. And here we're doing a definite integral, so this is our fundamental theorem evaluation. So we do our antiderivative, so we really have just done that in part B. So we would have negative x to the negative 1. We can use any antiderivative, so we might as well use the simplest one where c is equal to 0. And then we want to evaluate. So here we're doing our f of b minus capital F of a evaluation theorem. So, and this is, of course, negative 1 over x if you prefer to write it this way. So when we substitute our 5 and when we substitute 1, we've got this double negative. So remember that this minus sign is coming from the fundamental theorem. So, oops, and I put an x there. I guess I meant to put a 1. All right, so we have a negative 1/5 plus 1. So does that look like it'll be a 4/5? You can, of course, fix any arithmetic mistakes I might happen to make. And here we're doing the derivative of an integral. Yes, we have the same variable out here. We have a constant as our lower limit. So when we differentiate an integral, we undo and we get right back to the integrand, except we've replaced our variable. And then we have to remember our chain rule. If the upper limit is not simply k to the first power, then we've got to multiply by the chain rule. So here we've got sine of 10k squared and this 10k. I think I'll move in front here. And here we have an accumulator function. H is accumulating the area under another function, under some function of p. But notice we've got a problem here that our variable is the lower limit instead of the upper limit. So in homework, you don't in the future necessarily have to write this as a separate step. But remember, when we reverse the limits of integration, we get the opposite answer. So better safe than sorry if it helps you to write that step when we want to reverse the limits of integration. And now we're ready to find the derivative of the accumulator function. So now we're ready to put our upper limit here. So don't forget the negative sign out in front. That's an easy mistake to make. So we get back to our integrand, but now we've put x over 2 in there. And we have a chain rule on x over 2. That's 1/2 of x, so its derivative is 1/2. And we could do a little cleanup here, I guess. So we would come up with, well, I guess I could cancel. Oops, don't be so quick here. Order of operations. I just about messed that up. All right, so let's see what I've got right now. Negative 2x cubed over, do you see that? I almost forgot that that would be an 8. So maybe I should have expanded first and then done my canceling. So again, check that out in case I made a simple algebra error. And now we're comparing again our power rule for the derivative. So we bring down the 5 and reduce the exponent, as opposed to integration is an antiderivative. So we raise the exponent and divide by it and add our constant of integration. And now we change letter B as an indefinite integral. So notice we get a family of antiderivatives. So we get a family of functions when we do an indefinite integral. A definite integral is going to give us a constant. So now we're using our capital F of B minus capital F of A. So we've already found our antiderivative. So we pick the easiest one and evaluate it from negative 1 to 2. So we'll have 1/6 of 2 to the 6th. That should be a 64. Oh, and here, let's actually talk about this constant. Would it make more sense to move this 1/6 out as a GCF? So we could do 2 to the 6th minus negative 1 to the 6th. And then deal with that 1/6 at the end of the problem. So here we'll have a 64 minus 1, so 63 over 6 if my arithmetic is right. So we could reduce that to a 21 halves or write it as a decimal form. That is your choice. Question 7. Again, I think you've got the idea now. Are we integrating? Are we doing the derivative of an integral using that same independent variable? And is our lower limit a constant? So this is definitely fitting our fundamental theorem. So when we do the derivative of an integral, it's hitting the undo button, except we replace with that upper limit, and it has a chain rule of 5, and you could write that all in one step, I hope. Question 8. F is defined to be equal to the area under the tangent curve. So when we do its derivative, we're going to get right back to our lower limit. Can be any constant, by the way. We don't care about that constant because remember our proof, when we do the derivative of that constant, it will be 0 no matter what the constant is. All right, so all we need to do here is our upper limit into our integrand. So we will get tangent of 3x squared minus 5x, and then multiply by the chain rule would be a 6x minus 5. And you could move that in front of the tangent if you wish. Question 9. Derivative of cosine is negative sine of x. Antiderivative of cosine. Cosine is already the derivative of sine of x plus c. And then our fundamental theorem, our antiderivative is sine of x evaluated from 0 to pi over 3. Don't forget your unit circle. So sine of pi over 3 is square root of 3 over 2, a long leg, and sine of 0 is 0. The derivative of secant squared requires first a power rule. I don't know if I have room up there. I'll come down here. I bring down the exponent of 2, and I leave the inner glob alone. And then I multiply by the chain rule on secant. The derivative of secant is secant tangent. So we could write this as 2 secant squared x tangent x. Integrating, secant squared is the derivative of what? So our antiderivative, secant squared is the derivative of tangent x plus our constant of integration. And our evaluation theorem. So our antiderivative is tangent x, evaluate from pi over 4 to pi over 3. So let's maybe do a little quick review here of tangent. Remember, tangent is vertical leg over horizontal leg. So for square root of 3, we've got the long leg over the short leg. So tangent of pi over 3 is square root of 3. And pi over 4 is our 45, where the legs are equal. So we can leave our answer in that form. In number 11, we're doing the derivative of an integral. So we need to replace our variable with 8p squared. And then we need to multiply by the chain rule. And now you might put that chain rule here if you see what's going to happen here. That chain rule I just moved in front. Could you leave it in that form? Sure. You could have written this right away as 72p squared. Make sure you don't square the 8 here. It's only the p that is squared. And our accumulator function, this is really just to give you lots of repetition. So notice our independent variables match. We have a constant as the lower limit. We're doing the derivative. So we are going to come up with our natural log of x over 7 plus 2. And then I left space here instead of putting the chain rule in the back. Does it make sense to put the chain rule out here? All right. Derivative of e to the x, nothing to it, e to the x. Antiderivative of e to the x, still e to the x, plus a c. Evaluation theorem, e to the x evaluated from 0 to 3 would give us e to the third minus e to the 0. This is our capital F of b minus capital F of a. So we'll get e to the third minus 1. The derivative here, think of this as power rule. So we bring down the negative and reduce the exponent, or if you prefer, 1 over x squared, negative. Here we're doing the antiderivative, so 1 over x here, I guess we don't need to see any work here. 1 over x, I hope you recognize, is the derivative of natural log of x. And now, because this 1 over x is also the derivative, if we do a natural log curve with 2 branches, recall that the derivative of natural log of x was this curve 1 over x. But if we had the absolute value of x, that doubled our curve. So we've repeated this in class, but let me know if we need to practice this again. So this is the point here. When you put this absolute value of x here, then we have 2 branches. So this is the graph of y equals the natural log of absolute value of x, and y prime is 1 over x for both branches. And then I have to go back here. Don't forget to put your plus c. All right, here we don't so much worry about the absolute value if we're going to put in positive numbers anyway. Kind of takes care of itself. So this is the natural log of e minus the natural log of 1. So the natural log of e is 1, and the natural log of 1 is 0. And here we're doing the, I think I have a mistype here. Let me pause and see what I meant that to be. So this should read natural log of m, so that we have the same variable there. So the derivative of our integral, we will get back to our integrand with the w replaced with natural log of m. And of course these are inverse operations, so we will get m. And one more. G is accumulating the area under a function of s. Our independent variable matches our upper limit, so we're ready to do our derivative. So we're putting our upper limit into each variable, and we're going to multiply by our chain rule. So I'll leave a little space for that. So we're going to have 5 times our 3x quantity squared minus our sine of 3x, and our chain rule on the 3x. So I think we should write this a little bit nicer. How about 3 times 45x squared? And should we distribute the 3? It's up to you. No harm here distributing that 3. And I think we're done.